Okay, so I'm Phyllis Horner, and as I said, I'm helping Manfred Zapka, his assistant, as he offers this of the first of our four-part webinar series, which provides basic facts about building performance issues and the need to create more energy efficient and healthy building designs. This series is presented through a cooperation of the Environmental Research and Design Laboratory, ERDL, at the School of Architecture at University of Hawaii, and our firm, Sustainable Design and Consulting, LLC, through a grant made possible by Hawaii Natural Energy Institute, HNEI. We think the issues presented are very timely and important because energy efficient building design and healthy and comfortable buildings are increasing just as time passes. The importance of these concepts will just continue to rise over time. So the savvy professional will definitely have the edge if they get ahead knowing this information. On this slide that Manfred has up, you can see today's topic, but there are three others. We're hoping that you enjoy this one and that you sign up for our other three seminars to the extent you can. After the recording is finished, after today, we will send out to all of you who are on the call a link so you can replay it or share it. And eventually, we will be working with the ERDL staff to get it up onto the YouTube site that UH hosts. And if you're interested, we'll let you know then when that happens as well. So welcome. We look forward to our time together today, and I'm going to turn it over to Manfred Zapka to take it from here. Thank you.
Well, thank you very much, Phyllis, and thank you everybody for joining right now and also in future, whoever sees this as a recorded session. So on this, and my name is Manfred Zapka. I'm working with ERDL and HNEI, and we're really happy to present you this first series of 4 seminars. And this will be starting our cooperation on online presentation and learning. So you see on this side that our the topics of the 4 seminars we'll be having. And today we are speaking about energy simulations. And it will present some basics of energy simulations. Some of you will already know, but again, like this is intended for people who might not know it very well, but also for people who have done it, but would like to get a little bit of a second look. So the next page here, you see today's objectives, and why actually we show why building performance simulation, is so important and very helpful for us, because it can enhance our efficient, energy efficient building design, and but also while creating healthy and comfortable buildings. We'll be seeing that actually, we will be using building simulations to look at different alternatives, and afterwards we can optimize it and so on. And another issue which we also see that in the new kind of energy code, we can use simulations as a compliance path for the energy codes. Here in Hawaii, we have the IECC 2015, and in this one, the IECC 2015 offers simulation as a again like a pathway for compliance, and it affords the designer some kind of flexibility. So the overall central proposition here, value proposition, which we are going to show here, is that building performance simulation is an increasingly valuable tool for building designers and operators. So to create the energy efficient and healthy building which we use. And let's see, actually right now I just would like to share my story of the simulation, how I got into it. It was about over 20 years ago, where I started 3D animation simulation for plant design. And so this one actually developed in a sense that I got very excited, and I was very excited lately that working with ERDL and University of Hawaii on new kind of application of this evolving field. And the beauty in the simulation is that we can investigate alternatives of building design. We can optimize it even without before we put any kind of money into constructing it. And you will be seeing that the recent work of ERDL and university has used a simulation to study at various building design performance aspect, and energy performance will be, one of the highlights here of our presentation. So, and just take a little bit step back, because we always, especially people who have never done it, and I hope that the future will be helping, the local and also building industry to get a little bit more accustomed to simulation. When you step back, a simulation is not really very foreign, or it's not something which is new on the horizon, and it can right now it can be found in virtually every sectors of the industry. And here I will go through some examples. So on the left side, you see that, making cars very more aerodynamic. So you're reducing the resistance, make it more energy efficiency. You see like training pilots without leaving the grounds. This kind of simulation is sometimes supercomputers. You need really heavy computing power. But we see like architectural rendering. Almost everybody knows this right now. It's common knowledge, and it has been, like 20 years ago when I started, it was like, wow, you have something photorealistic things, you can put it into a neighborhood. So this one is also like a simulation, but much more visualizing. Floodplain simulation is that, right now it's very increasingly important. We see the effects of the global warming and climate change, that we get different rain events, so we can predict where is actually a good place to put the house, or where's like things we have to mitigate in order to avoid any kind of flooding problems in the future, so we are better informed. Next is airflow simulation. We have done that also. I will show you afterwards at the University of Hawaii here, specifically around high risers, where it has actually effects on the building itself or pedestrian comfort and safety. To the right of it, virtual reality application seems to be right now more the future, but it's increasingly used also for the energy, for the building design, and we'll be looking out for this. So it's not totally in the future. We might be there pretty soon. And last but not least, here we see the simulation of the hurricane path. This one is really like the high tech of simulation, supercomputers, but how important that is. I was not on the island when Lane happened, but I was following it closely, and it was pretty amazing how good the predictions were. So all of these, which you can see, simulations, and there are much more. And our building simulation is really a very small part of it, but the beauty is it can draw from a long experience, and will be even getting more sophisticated in the future. So here are some important issues right away to keep in mind for simulation. We always have to keep in mind simulation are abstraction of the real world. A lot of times get really like carried away and say like whatever we get out of the simulation is the truth. This is like, but it's not. And we can create the simulation more or less complex and with comprehensive calculation, but in the end, there is always simplification. And usually it is like that we have only specific performance behaviors we model, because as we see, our mathematical algorithm also is very close, is pointing to a specific behavior of the system. And we can only then take these numbers for the numbers which we create are only valid for this very specific conclusion. And simulation must not be very, complicated and complex if we define the application very, very concisely. And one of the things I also want to point out, and that simulation can predict performance of proposed designs under future environmental conditions. For instance, like climate change. I pointed it out that we might have to model how buildings will perform in the future, and when it's getting hotter, when it's getting humid, or if, for instance, there are big rain events, if the floodplain is still okay and safe. All right. So this is things we should keep in mind right away. And we have many types of building performance simulations. And sorry, I've got a little cold today. So starting on the left side, we have indoor comfort of a building. We have particles and pollutions where we can simulate the spread inside, whether or not it is actually an issue for health. And we can simulate sound, by attaching certain material properties of surfaces of sound sources. And very important right now, moisture in the air, moisture in the different building components. This actually is getting a very much attention, since more energy efficient buildings are having like moisture problems, which are not getting smaller. We can have airflow around and inside buildings, which we have done, with HNEI here, and we can simulate lighting and daylighting in a sense that how actually does the lighting or daylighting can replace artificial lighting, which of course creates also the need for energy. We can simulate thermal comfort, and right now here on the upper side we have energy, which right now we'll be concentrating on. If we say simulation is synonymous with modeling. So modeling or simulation is basically the same, and what we create again is like an abstraction of the nature of the real world, and we package it in a way that we can calculate. Okay. So we see the building performance simulation, there's a surprisingly broad range. We have seen that of existing and future application. And this is really a very nice and exciting tool. And we hope that actually, our contribution here in Hawaii specifically will make us such that, we'll be helping the industry to embrace simulation in a better way. Okay, so the main benefits of building performing simulation right now, I speak about the energy part, is twofold. One is financial incentives, where we can save energy costs, and the other one is code compliance. If we look at the financial incentives of energy simulations, we see that the more energy cost we can save through identified alternatives or optimized alternatives through simulation, energy costs go down. So this is great. We can try out. We are there. Multiple alternatives. We tweak here a little bit at the building. We tweak there a little bit at the building, and we come to a point where we have the most effective or the biggest energy cost savings. And the savings is like for kilowatt, what we say here, kilowatt hours, that's actually the energy, but we can also identify what kind of power we are using, kilowatts. And this is very important for why, because we not only have problems in providing energy, we have to save, but we also should save on peak energy demand. And so one of the things which happen is that whenever we want to save energy, it requires investment, and emphasis in energy efficiency measures. So if we are here from a simple, basic house design, we have to put money in order to save energy. So in order to get to more green or energy efficient house, right? You cannot get anything for free, right? You have to pay in order to save. So, and I apologize, I have to little cough today. So if we look at where we can actually, what the energy efficient measures are here in a building, these are just some examples. We can invest in roofs, or in cool roofs, which we are calling. Here, we configure the roofs in such a way that the least amount of heat is absorbed by the building. So it should just reflect the heat. It should be able to emit the heat so it should be cool. And I think the term says it all. It's cool roof. It's not cool because it's cool, but it's cool because it doesn't take so much heat, right? And wall insulation is similar, because here in Hawaii, usually outside it's hot, and we would like to avoid that the heat penetrates to the inside. We have insulation. So the wall insulation helps that we keep the heat through the walls out. And what it does, it's not only that, you know, we cool down like the inside walls, but then if the inside walls are cooler, we don't have so much radiant heat. And that actually that's what we are feeling when we are getting close to a hot object. Then on the left side here, PV, we can see an energy efficient measure is not necessary to save energy, but to create energy, to generate energy online. I think this is one of the most you know, amazing things which we can use with a building, that we can create energy. We use the roof to cut down on the energy demand, not necessarily in the house, but that we can create and offer some of the energy, you know, to the use on site, so that we don't have to take it off the grid. And the thermal solar, so we can save energy, since we do not have to create, you know, hot water by means of electric energy or gas. High performance windows, they make really a big help in terms of lowering the infiltration rates and also lowering the solar gain. So we have some kind of coating in there, but we also have, you know, insulation. High efficacy here lighting. This is right now very exciting. I see have the CFL. I even don't have the LED in there. And this is really a very powerful way to save a lot of energy, because the new lights, they're not only using saving energy, but they're creating a whole different way of using light inside of a house. And of course, one of the most important is that if we have AC, then it should be a very high efficiency AC. The more high efficiency AC is, the more energy we can save. But remember, when we said we have to pay dollars in order to save energy, here it is usually true that the most energy efficient and best equipment also costs money. So the whole thing we see, these are all, you know, examples of how we have to invest into issues that we can actually save energy. So then the next one is actually, how do we assess the ROI of energy conservation? So right now we are at a point, we have, you know, simulated, we have like a couple of alternatives which actually save energy. Then of course we have to see how much do we have to invest in order to realize the energy savings. And we have two kinds of ways we can identify. This is simple payback and net present value. We don't go into net present value right now, but these are the two different things. So you have first an initial investment, and then due to the energy savings, you regain this investment, and afterwards you're cash positive. And it's only like to say that, you know, these two things, like the simple payback should be used for shorter term return, shorter period return of the investment. And the longer it is and the larger the investment, you should use something like net present value. Again, like we don't go into the details, but please keep in mind. And rule of thumb is that the simple payback is almost more optimistic than the net present value. So when we actually decide on the final performance, we really have always to see that we have to consider both, not only how much energy we can save, how much is the investment which is needed to realize the energy savings. Okay, and we can say that you know, that building performance is a very effective assessment tool, and it is it is very effective and good way in order to identify the most effective way, just to try out all these alternatives and see what is best in terms of the finances. There's also different other benefits where we can actually see that we can comply with compliance standards, codes and building standards for LEED. For instance, we get points if we can see that the simulations lead to good energy efficiency, or as I said, like the International Energy Conservation Code, which will be or is already adopted by Hawaii, offers one compliance part of the, as through simulation. So simulation always start with systems, and the systems actually is what we see like an abstraction of the real world. And it's important to see them both, if you can create actually the simulation of if you see the results. And the modeling and simulation of a system is a calculation method of using the mathematical models to predict the performance of a system. This is important. You have the real thing here, and there's some kind of mathematical algorithm which actually defines some kind of prediction. The nice thing, we don't really have to know all these mathematical mathematical algorithm in order to use the simulation. And how can we calculate the system performance? How can we quantify it? It actually is, we can do it either pencil and paper when it's very simple, and we said like it could be relatively simple. We can have a spreadsheet, but the best would be some kind of a building performance simulation software. And that's actually what we're doing right now at ERDL, and that's actually what we would like to do in future to also help the local building industry to get more into. And if we very briefly speak about what is a system has three elements: a function, elements, and interconnection. Okay, this is actually the house, and the function of the house is to provide healthy, safe, and cost-effective shelter and uplifting place to live. We should always keep in mind, even if you make it very energy efficient, in the end, the value of the house is that it is healthy, it is safe, and is cost-effective. A building elements is like, like the house has all kinds of elements. It has internal rooms, it has appliances. Here we have a vehicle, it's of electric. We have AC, which is cooling the building. We have different kinds of renewables. So these are all different systems, and the systems are, we also have systems in systems. And the beauty is that actually in our energy model, we take it as such that, there is something like a boundary, and we can identify, the quantitative measure of the system by just drawing a boundary around this. We don't necessarily have to know everything which goes inside in this system. Okay. So what is the system here? For instance, interconnect, where are the boundaries? The boundaries would be the red. Interconnection is that it has to get some kind of electricity, and the outside of the system is the grid. The inside is all the different components. Whereas here, for instance, the PV can even give electricity also to us. So a lot of times we have like the black box, and this is right. We can define the quantitative performance of the black box. That we have an input, we have an output, and there's something going inside of that black box, and it's consumption, generation, and storage. And now I throw something onto you, which is like like an equation, right? And so this actually is like an energy balance of the space. And whenever we look at simulation and we look at the results, what we get numbers. And the numbers actually will tell us, how much, for instance, do we consume? This is going into our system. How much do we generate if we have PV? And here, how much do we consume? Either we can total it all up and say, this is actually whatever we consume inside, or we can identify different components of the system. What actually is what we are consuming here. And if we have like a surplus electric energy, we can also export some electricity to the grid. So this is actually this will help us to identify, what is coming out of the simulation. We don't necessarily have all to know the intricacy inside of this thing. We just say it's convenient. We have a boundary, what goes in, what goes out, what is consumed or generated inside. Our home, for instance, is a very net energy. We create a lot of here at our home, we create a lot of energy. So we would actually export, electricity. So the use of software, different aspects. What I said, we have energy, we have thermal comfort, we have daylighting. There are different ways we can use in order to identify the performance, and all of them are actually important if we want to make sure that our system, which has a certain function, as we saw, like the system of a house has a certain function, that it creates a comfortable, energy efficient or cost efficient way to be. It has to serve this purpose. So if you right now compare building simulation with actual measurements, which is often done, so we actually simulated one side. That at one point we also would like to know how does it compare to the actual reality. And a lot of times we are surprised. Hey, you know, this thing does not exactly, you know, is not exactly coming out as the real world. And we always should keep in mind that the simulation are the abstraction of the real world. And it also is important to see how much, how much complexity does our simulation have. You can use maybe very complex. Then, you know, at ERDL, we took some simulation. They ran a couple of days, but we could have something which is like in a minute, it's power, or it's done. Power is what we say here in Hawaii. So, but the power actually for the simulation is not necessarily only how does it actually compare to the real world measurements, but how is the relative performance. So we have like a benchmark which we simulate, and then we have the different alternatives. But it should really help us as designer to plan, and we should not really shy away. We should embrace the simulation more and more. Here are just some examples which we would measure. If again, like sometimes it makes a lot of sense to measure, and we have the electricity, you know, some other things we can measure: the temperature inside of the building, humidity, air movement. And what we can see here, like it's a different way of getting to it. It's like the energy we would have, like the big black box where we call the whole house electric consumption. Basically here we say, what is the whole house, what is the whole building actually consume? So we have an input, we can measure the input, and if we have PV, of course, we can also put the output. But if we don't have PV, this would be actually our biggest result. How much energy is used for this entire building if we have the black box model for the entire building. The next one would be if we want to measure the electricity used by the specific or generated in terms of PV here for the different elements of the building. And here you see it could be like the large appliances, you know, the plug loads, you know, how much does the HVAC means, you know, consume for the building, and domestic hot water, how much do we have to put in terms of electricity to power all the pumps, but how much actually do we save in order to heat up the water? How much actually do we have for lighting? So here it's much more that we can go in there and see how do our simulated results compare to the actual measurements. So we get a good idea, you know, where is it maybe a little bit shy. It does not really say that the simulation is not really doing well, but you know, again, like we should keep in mind there's certain abstraction to it and simplification. And the simplification makes a lot of sense if we actually know what kind of simplification we need or we are using. So the measurements, again, like we said, sorry again. What we have, like, I just wanted to give you a short example. What we also at ERDL, you know, do a lot of times to go in and measure. And so we have the relative humidity. We have a globe thermometer. A globe thermometer is measuring the mean radiant temperature. This means in how much all the different surfaces in the building actually emanate. Because as we are in the building, we are feeling the heat coming from the radiant heat coming from all the surfaces. What the internal temperature, air temperature is, and what kind of wind. These are the typical the things which we use in terms of the indoor environment. There are other things like CO2, carbon dioxide, or VOx, that we can also measure in order to identify the healthy issues of the building. So I just wanted to go right now and just make it a little more realistic, show you some applications which we have done here at ERDL in the last couple of years. And this is one of the things we have measured is for external airflow investigation around naturally ventilated buildings, and with CFD, and CFD means computational fluid dynamics. This is actually a very exciting field, and a lot of people shy away because it sounds complicated. And I agree, sometimes it can be very complicated, but it really also gives you good results if you are interested in airflow, in very specific properties inside of a room. Then you would use computational fluid dynamics. Here in our field is on the left side, you see here, this one is the Manoa campus. And we, at this point in the project, we were investigating the airflow around Keller Hall, but also going through that is the next slide. And here you see these different shades identify what is the magnitude of the wind movement here. When you see very red is very high wind, so the wind here coming here, this is like from up Valley Manoa and going around Kennedy Theater. You go Keller Hall, for instance, between Keller Hall and Kennedy Theater here on the left side, we measured in and see how good was our prediction. This is an internal CFD where we identified what is the air movement through a building, and we checked it how well we could predict it. This is very important because air movement through buildings, naturally ventilated buildings, basically gives us cooling, gives us fresh air. And the next slide shows not only we did air movement, but we used CFD here to predict thermal comfort. And you see here, this one on the left side, this is a model, but this is the 3 model which identified the computational domain. So whatever is inside of that domain actually is calculated. What is outside is not existing. The computer cannot see it. The below is here like, this would be like a ceiling fan, the white thing. And here you see the different contours indicates how much airflow there is, because airflow over the body acts like a cooling mechanism. So this one was pretty interesting. And on the right side here, we saw the real test setup where we measured and tried to verify our results. So the last one is here. This is an energy simulation for residential houses, which we've been doing at the University of Hawaii for quite some time right now. This is using a software which is called BOPT, and in our next webinar next week, we'll be going through a process of using this simulation. That's a basic simulation, energy simulation software, to show you how the generic process is. And here you, for instance, up here you could see there's always like you make first a model. This is a geometric model, and then you get some kind of results. And you see here lower here, this would be a result. This show you in overall how much energy you use, but it also shows like, differentiate about the different components inside. So here you get the whole house, but you get also an identifier, what is used. And here, for instance, it is used that we have a reference case and we see some kind of alternative. The proposed design, in our case, we could significantly lower the energy use for our proposed design. So we were very successful. So let me just go very quickly here what lies ahead of building performance simulation. And I would stipulate that it's really increasingly support design and operation buildings. And this is actually, and it can really increase your proficiency as a professional, not only as a design professional, but also as a professional, for instance, if you want to operate a building. So it makes a lot of sense in order to get through it. And the wonderful news is it's not getting relatively harder, but it's getting more intuitive. So the interface is getting more intuitive. The hardware and the software is getting more powerful. It doesn't store that much. Not that, for instance, sometimes, and when all the way back, when I started, some things were going for a week, and all of a sudden the computer starts. Oh no, I have to start for another week or so. And again, like the new generation of the building designers and professionals who are right now just in university or so, we hope that they are getting very, very well familiar with simulation tools. And so you will probably see a big shift in the industry as everybody is getting much more savvy of using these things, and also getting more intelligent in terms of using it. So just what actually is, how has building performance simulation developed? It started all the way back in the 1950s. Here you see, like, this is a big a computer just fixed. I think it's just for the whole house was full of the computer. Right now we have a small iPad. But first was like academia, it was restricted. But right now it's like such that it's getting more and more to, basic and wide use for design and construction professional. And here's some areas which we think, building performance simulation will play a bigger role in the future. Well, of course, important for Hawaii, energy efficiency and conservation. And so we can do a lot in order to really come up with very high performance, high energy efficient buildings. And we can also see that the energy code compliance, and we see that Howard Wick is also on the call. He has been instrumental of pushing the new energy code forward for Hawaii. And we have there like a code compliance path that using simulation, that the simulation offers much more flexibility to the designer to come up actually with new designs, and we are not so much limited to a prescriptive path. But we always have to keep in mind, whatever we do in terms of energy efficient, we also have, it is important to have wellness, health, and comfort in a building, because the value to the owner, to the occupant of the building is, very much in terms of how it actually is the building conforming to indoor air quality. And so we have indoor air quality, we have humidity problems, we have thermal comfort, we have daylighting. So these are all different things which help very much in terms of having wellness and health and comfort in a building. And we think, at ERDL, we think one big challenge actually to achieve comfort is, while also conserving energy, is really central. And this is central to the designer, because on the one side, yes, we really have to be very efficient in driving down energy efficiency, but on the other side, we also have to have good and healthy buildings. And the next things which we'll have, like the envelope performance of the building envelopes, are getting more and more complicated. So we need really, very encompassing simulation tools in really to see good optimization potential for the thermal envelope. On the other side, we can size building mechanical system much better. We can optimize it, and we can also use innovative technology, not only like how much energy it will use, but what kind of consequence does this innovative HVAC technology have on our comfort. And there are many more, but I just have one more which fits on the page: the smart grids interacting with buildings. This is actually something which is very important in future, as we have more and more distributed energy and smart grids in order to keep the grid stable. There are two kinds of simulation software we're actually looking at. And one is the integrated software performance, all different, this is actually something where we first, we create a model, a geometric model, and we can then simulate and get ideas about energy, daylighting, heat transfer, thermal, and airflow. And on the other side, and we have standalone building performance software, where we have dedicated software for any kind of that kind of stuff. The advantage here, we have one model. It's relatively easy to do. Once we have the model here on the other side, we might actually have to model multiple times if we cannot, create the model. And I see right now the geometrical model of the building. So the main differentiator is either the accuracy, which is better in the standalone and dedicated software, and the ease of use, which is the integrated. And I'm actually closing right now with one message, which I've learned also by working with people in the simulation field. Don't take, the simulation as the real world, and whatever comes out is like the gospel. And we always have to keep in mind the simulation is an abstraction of the real building here, of the real situation. And so whenever we look at simulation, we should also have some kind in mind that we have an idea how the building would actually react without the simulation. And first get some kind of what we call like the building story, like the building energy story. We already can identify, we can predict, or we have an idea before what direction should the building go, and then we use the simulation to really quantify how good would it be actually what we try to assume. So I just summarize very quickly here, and so right now we have that we stipulate the simulation of building performance plays an increasingly important role for the building design, operation, and code compliance. And so it is actually important for us to go there as professionals. It will help us to make more valuable professionals. And the modern simulation tools they're very effective, and they're getting easier to use. We can use very powerful interfaces in order to build even complex models. There has been very in-depth calculation. A lot of these algorithms, which are sometimes sophisticated, have been validated. So, and the third one is not only about the simulation, but it also tells you that you should not really step back and always use simulation for everything. It always pays in to have a good understanding of building physics and the ability to develop a hypothesis. That's what I think the building will do. And that's actually what we're doing at ERDL. We are not only, trying to teach, how to simulate also what is behind it. And I think it makes everybody, who uses and interprets simulation a better, how is it, simulator? It's not right. We are not the simulators, right? We are people who are using the simulators. So, and by this one, we go into the Q&A. Thank you very much. Sorry for the